Up to this point, when we talk about derivative, we think about slope of the tangent line at a point or rate of change at a point. And graphically, it looks like this. I have a graph here and a couple of points, and the derivative at this point would be the slope of the tangent line at that point or the rate of change at that point. And for this point, the slope and rate of change at that point would correspond to the idea of derivative. Well, suppose, though, rather than a change at a point, we want average rate of change over a particular interval. That is, we're thinking about, gee, what's the average slope then between these 2 points? That is, in this interval, you see, what's the average slope? Well, it's this slope, that slope, this slope. Of all of those slope values that are taken on, you see, by this meter stick, then what's the average of all of those? Well, it turns out that the idea is pretty easy. It is, the average slope then, is the slope of this line, the slope of the line containing those 2 points, it turns out. And that's all there is to it. And we've seen the formula for this before. It's just the slope formula. So the average rate of change in the interval is just y2 minus y1 over x sub 2 minus x sub 1. And let's talk a little bit about various notations associated with this. Sometimes the notation itself can seem confusing when really it's very consistent with stuff that we've had before. That y sub 2, now the y x1 and 2 and y1 and 2, let me label those here. Here's x sub 1, x sub 1, y sub 1. Here's x subscript 2, y subscript 2. So that's the idea. And the change in y, you see we're changing these y's, changing x's downstairs. You see, and we've done that many times before in calculating slope. But just understand that y sub 2 is really f of x sub 2. So it's just another notation that can be used here. For y sub 1, it could be f of x sub 1. You see, and another notation, an even simpler one, and one that we'll use quite often, is that this difference in y values is nothing more than a change in y, change being indicated with the delta. So delta y over delta x then for this average rate of change. Another notation, and one that's often used in textbooks, is this. If we're talking about a point A and a point B, then the average rate of change in the interval is f of b minus f of a over b minus a. You see, just another, but very consistent with these others, but just another way to do it. Let's take a couple of problems. The concentration C in milligrams per milliliter of a drug in a patient's bloodstream is monitored in 10-minute intervals for 2 hours, where T is measured in minutes. Now here's T, and here are the 10-minute intervals, and here's the concentration of this drug in the bloodstream, and these concentration amounts are in milligrams per milliliter of blood. See, milligrams of the drug per milliliter of blood. See, that's the idea. We want to find the average rate of change in the concentration over each interval. So we want the change in concentration in the interval from a time of 0 to a time of 10 minutes. Now there might be some confusion at first about the idea that we use notation over there that had a lot to do with x's and y's and a's and b's and so forth. We had a graph to work with. We don't see a graph right here. We don't even see a function, you see? So how do we know which one to put in the numerator and denominator? That sometimes is a question that students have. And you go about thinking about that idea by considering what letter in our problem takes on the role or plays the role that x would play and which one takes on the role of y. It's not always very, very obvious, but in this problem we have an x-y idea, Tc. So concentration is a function of time, if you will. But at any rate, the T is playing the role of x and the C is playing the role of y. So when we think about delta y over delta x, for this problem it is a delta C over delta T. And let's make our calculation. Now in this interval from a time of 0 to 10, here's 0 to 10, the change in concentration is from 0 to 2. Now when we take that difference, we use values that are at the end of the interval. So we're using 2, minus 0 for the change in the concentration, and 10 minus 0 for the change in time. So this is 2/10 or 2/10 like this. Now the unit associated with this is notice it's concentration over time, so the concentration amounts were given in milligrams per milliliter, and then time is in minutes. So this is milligrams per milliliter per minute is the unit. For this interval from 0 to 20, from 0 to 20 minutes, you see we have a change in concentration from 0 to 17. So again, we set up our idea of delta C over delta T. The change in concentration is 17 minus 0, and the change in time is 20 minus 0. And so it's 17 over 20, and that turns out to be 0.85. And again, it's 0.85 milligrams per milliliter per minute. Suppose we want to talk about the interval from 100 to 110 minutes. 100 to 110 minutes. On the chart, it's 100 to 110. The change in concentration. Now notice that the change in concentration, the concentration is sort of dipping off here at this part. If we look at the values here, they increase up to 113 and then begin to decrease. And so we have a decrease in the concentration over this interval. And that'll manifest itself in a rate of change which is negative, as we might expect. But the change in C is 103 minus 113, and the change in time is 110 minus 100. So that's negative 10 over 10, or negative 1 milligrams per milliliter per minute. Let's talk about average velocity. Average velocity is actually related to some things that we have experienced in the past, and I want to point this out and kind of underscore it here, because a lot of students feel like in calculus we introduce a whole new language and it's a whole new mathematical system, but it certainly is related to everything that we've had before. If you think about distance as rate times time, and if I solve for rate, its rate is distance over time. So rate is distance over time, and it turns out that average velocity is related to this idea. The average velocity is change in distance over change in time. And that's really all there is to it in the calculation. And it's not as though we're doing anything patently different from our intuitive idea of this notion before. I mean, if you go from one place in a city to another place, let's say you travel for 40 miles and it requires an hour, then what's your average rate? You went 40 miles in an hour. Oh, it's 40 miles per hour. You see, that's your average rate for that journey. Now, in some part of it, if you got up on a toll road or something like that, you might have gone 65 miles per hour in part of it, and at part of it you might have sat at a light, and the velocity at that point would be 0. But the average velocity, or the average rate, was 40 miles per hour. You see, and that truly is all there is to it. Now, in this problem that we're talking about here, we're talking about dropping an object. So we have a free-falling object, we're assuming no air resistance, and here is the formula or the equation or the function which relates height to time. So height now is a distance, and time is as we understand it, and time is in seconds here. And we have information that comes from this relationship. Now this object was dropped from 100 feet up. And you know that when objects are dropped, the gravity works on it, and gravity keeps working on it, so it accelerates. It changes speed or changes velocity as it drops, because gravity keeps pulling on it more and more and more. And if air resistance doesn't affect it, it continues to gain speed all the way to the ground. Now, this kind of model would be very true for an object such as a cannonball, which doesn't respond very much to air resistance at slow speeds. But with a feather, it wouldn't be a very good model, you see, because a feather is it does respond quite a bit to the air resistance. Anyway, let's see. We have so we have this. Now, in filling out a chart like this, just replace the values of t within the expression and find out the subsequent value for h. For 1.5, for example, replace t with 1.5, square it, multiply by -16, add 100, we get 64. You see, and that's how these values come about. Now let's find average velocity within particular intervals. Now, I think it's important to know that with free-falling objects, once again, that it starts out at a velocity of 0. When you first drop it, it isn't traveling fast at all. And then it gains velocity as it goes along. It gains speed as it drops. So in an interval which is at the top of the drop, which would be up here, this is kind of a long interval at the top of the drop, you see we have a certain average velocity. Now, how might we think about it should change if we narrow the interval from the same point? You see, from 1 second to 2 seconds, this is from 1 second to 1.5 seconds. Are we going to get an average velocity that is slower or faster than this? Well, it turns out that at 2, it's going much faster than it was at 1. The average velocity here is going to be higher than the average velocity here. And as we tighten up from 1 to 1.1, you see it's actually the average velocity is going slower and slower if we maintain this first item in this ordered pair. Now, I like to point out things like that because it gives us a big picture feeling for the problem that we have before us. But very specifically, here's how we make the calculation. In the interval from 1 to 2, we want a delta h over delta t. Now remember, this is a change in distance over change in time, which is what we talked about as a relationship over there. So change in height over change in time. Now, for the change in height over this interval from 1 to 2, so from 1 to 2, the change in height is 36 minus 84. You see, so we just read it right off of here. Away we go up here. 36 minus 84. Change in time is 2 minus 1. 2 minus 1 is 1. 36 minus 84 is negative 48. So it's negative 48 feet per second. The negative tells us that the object is falling. Okay, in the interval from 1 to 1.5, same idea. We look over here at the chart 1 to 1.5, and the change in height, the height values are 64 and 84. That's a difference of, looks like 20. So over here, change in height, 64 minus 84 is negative 20. And 1.5 minus 1 is 0.5, we find then that the average velocity in the interval is negative 40 feet per second. Notice that it's a smaller number than this one up here. The average velocity is less. Okay, and then from 1 to 1.1, you see, let's see, again, 1 to 1.1, the difference in heights are 80.64 minus 84. So here we go, change in height over change in time, 80.64 minus 84. When we do our calculations, the change in time is 1/10 of a second, and dividing we find the average velocity to be negative 33.6. Now, on all of these, we're finding average velocity from the velocity from 1 second to another point in time. Suppose we change the beginning of this interval. Suppose rather than from 1 to 2, 1 to 1.5, 1 to 1.1, suppose we think about changing and coming down here to like 2 to 2.1. This change, this is a 1/10 change. We had a 1/10 change over there. That might be interesting to see what that difference is. And we know that the object is gaining speed all the time as it drops, because that pull of gravity is causing it to go faster and faster. So the average velocity in here we would expect to be larger than these other average velocities that we've calculated. And we make the calculation in the same way, and the setup of it is the same as we had over there. It would be a change in distance or a change in height over a change in time. And the change in height, well, I'm reading right off the chart, it's 29.44 minus 36. And the change in time is 2.1 minus 2. So performing the calculations, we find that this average is negative 65.6 and it's feet per second. So it is more, as we would expect. Here's the position equation that we used in the previous problem. Let's talk about derivative. If we take the derivative of this function, we get h prime of t is negative 32t. Now, our interpretation of derivative up to this point was in two parts, or in two ways. One is slope of the tangent line at a point, and the other is rate of change at a point. Now, when we talk about rate of change at a point, it's the rate of change in whatever it is that we're taking the derivative of. Now, this is a height equation, so it's the rate of change in height that is the interpretation of the derivative of a height function. So, rate of change in height at any particular point in time. Now, an object was being dropped, remember, the rock or something like that was being dropped, and if it is a rate of change in height at a point in time, rate of change in height, oh gee, that's velocity. So really, when we take the derivative of a position equation or a height equation, it gives us a velocity equation, and that's what this negative 32t is all about. So if we want to find the velocity at a point in time that is, let's say 2 seconds after the drop occurs, then that velocity is negative 32 times 2, or negative 64 feet per second. By the way, just as a sidebar here, the relationship between velocity and speed is very close. Velocity generally has a direction associated with it, but speed doesn't. So speed could be thought of as the absolute value of velocity. That's just one way to think about it. Now, let's generalize the situation a little bit. The general position function is this. H is negative 16t squared, which we saw in the previous problem, then plus v naught t plus h naught. Now, v naught is the initial velocity and h naught is the initial height. Now, in the previous problem, the object was being dropped, and so v naught, the initial velocity, was 0, so there was no middle term here. And the h naught was 100, and that's why we knew that the object was being dropped from 100 feet. All right, now, suppose we take this general position function and take its derivative. You see, take the derivative of this, then we have the negative 32t from this term, and then we have v naught. You see, and this then is a general velocity function. Well, let's use this idea in this next problem. It says a diving board is 32 feet high. The velocity of a diver springing from the board is 16 feet per second. So the diver is going up at 16 feet per second. We want to answer two questions. One, when does the diver hit the water? And number two, what is the speed at impact? Well, let's see. In order to do this, we have to use our general position function and make an equation related to this problem. Let's do that. So we start out with our general position function, and we replace v naught, the initial velocity, with 16, and h naught with 32. V naught 16 because the diver is springing off the board at 16 feet per second, and h naught is 32 because the height of the diving board is 32 feet. All right, so here then is our height equation. Now, when does the diver hit the water? When does the diver hit the water? Let's see, we have a relationship between height and time here. When the diver hits the water, the value of h is going to be 0. Oh, that gives us a clue as to how we can figure this out then. You see, just replace h with 0 and solve this for t, time, and we'll have what we need. All right, let's do that up here. So the a part, we start with our height equation, and we replace h with 0, and then we solve. Now we see that we have a quadratic relationship, so we solve by factoring, take out the common factor negative 16, we're left with this. Factoring the trinomial, we get t minus 2 times t plus 1. The zeros of these two factors are, let's see, to make this factor 0, t would have to be 2. To make this factor 0, t would have to be negative 1. Now, t stands for some amount of time, and it doesn't make sense in the problem for t to be a negative value, so we throw that one out, and t equals 2 is what we're looking for. So after 2 seconds, the diver hits the water. Now, what is the speed at impact? Well, speed, velocity, that's the idea. So we want first derivative. So we take the derivative of our height equation, and it turns out to be h prime, or velocity, is negative 32t plus 16. Now all we do is pop in the information about the time at the point of impact. You see, we said that it's going to take 2 seconds. After 2 seconds, the diver hits the water. So we find the velocity after 2 seconds. So replace t with 2, and we find that velocity to be negative 48 feet per second. The speed then is 48 feet per second at the point of impact. In business and economics problems, we use words like profit, revenue, and cost. And now we want to introduce the idea of derivative into this environment, and when we do that, we're thinking about rate of change. Well, all we need to do in thinking of rate of change of profit, rate of change of revenue, and so forth, is introduce the word marginal, because rate of change of profit is called marginal profit. Rate of change of revenue is called marginal revenue, and rate of change of cost is called marginal cost. Now, understand that this is a derivative idea, so marginal profit would be the derivative of the profit with respect to X number of units. Marginal revenue is derivative of revenue with respect to X number of units. Marginal cost, derivative of cost with respect to X number of units. Consider this problem. It says the profit derived from selling X units of an item is given by this equation. All right, so here we have a profit function. Now notice that it's profit in terms of X units sold. Now the A part says to find the marginal profit for a production level of 50 units. Marginal profit. Well, to find marginal profit, it's the derivative idea at a certain production level or a certain level of sales, and that would be 50 units. So let's see, it would be, we want to find P prime of X, and that turns out to be, let's see, turns out to be this. And now all we do is pop in the number of units that we're talking about. So a P prime of at 50 would be this. And away we go. And we find this value to be $11.50. So this then is the marginal profit. And we can kind of think of this as the rate at which the profit is changing at this particular point in our sales, in our graph of sales. Our graph of sales may go from 0 to 5,000 or something, but at this level of sales, at that particular point in the sales curve, we are talking about a rate, a profit rate of 11.5, or a marginal profit of $11.50. Now, suppose we want to find the actual gain in profit. It's a good comparison to look at these. Find the actual gain in profit by increasing the production level from 50 to 51 units. It ought to be pretty close to this. You see, and to find the profit at 50 units, we use our profit equation and replace X with 50. And performing indicated operations here, we find the profit at 50 units to be $525. The profit at 51 units means that we would just replace the X over here with 51, and punching the calculator a little bit, we find the value to be approximately $536.53. So here's the profit at 50 units, here's the profit at 53. The difference in these two, you see, by increasing sales from 50 to 51, you see we get, let's see, the difference is $11.53. So this idea of marginal profit is a very close approximation for this actual value. And we're using a somewhat simpler function in order to make the calculation. Well, let's turn our attention now to the notion of demand. And we mentioned, we may have mentioned demand and supply a little bit in the past, but it was in a different context. Now, understand this, that a demand function has everything to do with changing price and changing the number of items being sold and that kind of thing. And the idea was that if you reduce the price, then you sell more units. But the notion is that if we can express price as some expression in X units, then that is a demand function. Now, from that demand function, you can calculate revenue by taking X number of units and multiplying times the price. You see, X units times price G, that gives revenue. Just a very intuitive idea. Now, let's make a demand function here. And this is not a trivial kind of thing, but just follow me through this. It'll take a little practice to where you can do this on your own. But suppose that 2,000 items per month sell at a price of $10. And suppose that it's projected that sales will increase 250 units for each 25-cent reduction in price. For every 25-cent reduction in price, we're going to increase sales 250 units per month. Now, how do we write that down? Well, here's what we do. Here's the demand relationship then. It's 2,000 items sell right now, and we're going to add 250 items per month. Let's see, for every 25-cent reduction in price. Well, gee, how many of those would there be? How do we calculate that? How do we express that idea? Well, the price that's established to begin with is $10. That's the basis upon which this 2,000 per month are sold. But if we take $10 and subtract the new price, some amount for a new price, that this reduced price, you see, and then divide by 25 cents. In dividing by 25 cents, we're finding the number of 25-cent increments in this difference. You see, if we reduce this $10 price by 50 cents, that's two 25-cent increments. Let's see how it's figured out. It's $10 minus $9.50. Oh, that's 50 cents here. Divide 50 cents by 25 cents. Oh, that's 2. That's 2 of these 25-cent increments. The 2 is multiplied by times the 250. You see, so this is how the calculation is made. All right, and this then will give us X number of units which are sold. Now, you may notice here something kind of peculiar, that up at the top I said that the demand function is price in terms of an expression in X, but gee, here we have X and some expression involving P. So we have to go through the process of taking this equation and solving it for P. You see, now, solve this for P and we have P equals 12 minus X over 1,000. Okay, now once that's done, we have price in terms of X number of units. And then once we have that, we can make a revenue calculation. The revenue function then is revenue is X number of units sold times this particular price that we're talking about, this expression for price. So X times price, the price expression is 12 minus X over 1,000. Multiply X times both terms, we find that the revenue is 12X minus X squared over 1,000. Suppose a fast food restaurant has determined this as its demand function for hamburgers. And notice its price in terms of some expression in X. We want to find the increase in revenue per hamburger for monthly sales of 20,000 hamburgers. Now, this is a sales level of 20,000 hamburgers. The increase in revenue per hamburger, the rate of change in revenue. You see, it's the same thing as saying find the marginal revenue when X is 20,000. That's what this is. All right, we start with the demand function. Price is 60,000 minus X over 20,000. Now, revenue is X times that expression. So it's just X times all of this. And now we just clean that up a little bit and get it ready for taking derivative. Now, notice what I've done here to clean it up. I've multiplied X into this numerator. It would give us 60,000 X minus X squared. And then I'm going to snag out that 20,000 denominator just by factoring out 1 over 20,000. You see, so that's how that 20,000 came out, and then the X goes into that numerator, and that's why this expression takes place. And then the derivative is pretty easy to calculate. We find the derivative to be this. And now, using that derivative function, we can find the marginal revenue at a level of X equals 20,000 just by plugging into it. So the marginal revenue is found by replacing this X with 20,000, evaluate, and we find the marginal revenue to be $1 per unit. Now, let's extend the idea. Let's take the same problem and extend it a little bit, and let's say that the cost of these hamburgers is, the cost equation is 5,000 plus 0.56x. And this is for X values that are between 0 and 50,000. Okay, suppose we want to find the profit and marginal profit for X equals 20,000 units. Well, okay. Now, the profit, we know that we just use our basic understanding of the relationship between profit, revenue, and cost. Profit is revenue minus cost. Well, let's see, profit then is revenue. Oh, the revenue function was over here. We just kind of bring it over. Here it is. And then minus cost. The cost is given up here. And that's this expression, just brought down. And now we clean this up a little bit. So we go through and perform the algebraic manipulations of simplifying, and we get this. Now, so this is profit in terms of X number of hamburgers sold. Now, so here's the profit function, but for 20,000 units, well, the profit for 20,000 means replace this X with 20,000, replace that X with 20,000, and evaluate. We find the profit to be $23,800. Now, what about marginal profit at 20,000 units? Well, marginal profit is before we go over there, wait. Take a look at this. We're going to take the derivative of this, and I just want you to see it because it's fairly easy to take the derivative of this expression. And that derivative we find right over here. The derivative of P with respect to X is 2.44 minus X over 10,000. So at 20,000 units, the marginal profit is found by just replacing the X up here with 20,000, and we find that marginal profit to be 44 cents per unit. Now, this is the manipulative version of this problem, but the problem goes a little further. I mean, we can think of this in practical terms and what it means to make this calculation and why it's important to make the calculation. And it has everything to do with this. Let me back up over here and create a little room. So if the profit graph is quadratic like this and it's parabolic, then at some number of units sold, we have a rate of change at that point. We have a derivative, a slope of the tangent line, or a rate of change in profit that is what we found over here. Now, 44 cents per unit is a positive value, so there is a positive slope of the tangent line at that point. There is a positive rate of change at that point. But notice that because of the nature of this graph, there is some point where the number of sales will give a profit amount such that the marginal profit is 0. The slope of the tangent line, you see, the rate of change, you see, is 0. And there is another point over here, a little bit farther over, and I'll emphasize the point here with this as rate of change, you see, at a point. And over here, we are selling more and more items. Well, gosh, we end up in a situation where the marginal profit turns out to be negative, you see. And that's why all of these calculations are very important. We'd like to know where these points occur in the process of increasing the sales for a business like this.